Thanks for coming here, and my name is Usman Sarood. I'm the Infrastructure and Distributed Teams Lead at msgs Systems, and I'd be co-presenting this talk with Chunky Gupta, who is a fellow Distributed Systems Engineer, and we're going to be talking about how to cost-effectively and reliably aggregate messages using Kafka. So just a little bit overview about what we do. So we are a Wi-Fi startup. We ingest a lot of telemetry data from our access points, and since we're doing indoor location, we also ingest data from mobile phones to track them in real time. So what that means is we have a bunch of these access points lying in outside world along with mobile devices. All of these devices are sending continuous messages every few seconds, depending on what kind of message it is, and those messages get buffered into Kafka. And we then take those messages and we process them in multiple different platforms. Some of the real-time processing happens in Apache Storm. We also have some real-time processing happening in Mesos. And Mesos is also the resource manager, which is hosting all of our API and some other stuff which is not non-real-time as well. And we're using, we're using a couple of different databases. We use Cassandra for time series stores, and that's where all our aggregated data goes. And we're also using Redis for some short-term cache, as well as recently we started using Elasticsearch as well. And but in this talk, I'm going to be focusing on live aggregators. And just to give you an idea about just to set some context, we are a company who are very big on reliability. And 80%, or actually even these days probably more than 80% of our entire production data center, it runs on these Amazon Spot instances, which are volatile in nature. They come at a significantly reduced price. So if you think about it, our costs are very low. We are typically 70% cheaper than whatever other companies can get by reserving machines. But what that means is that we have to be very, very fault tolerant, because we get lots and lots of servers going away over the course of a day. Okay, so let's focus on one of these boxes over here, which is our aggregation system. And that aggregation system forms, it's a significant part of our data center, which constitutes for a lot of compute that we use. Before I go into the details, I wanted to acknowledge our team who's working on live aggregators. Amarinder Singh Mindra, he's done a lot of cool work with live aggregators. And we have Ibrahim, who's from the data science team. He's writing new aggregations on live aggregators. He's been doing that for a few months. And Jitinder, who basically helped a lot when live aggregators was in the very initial phases. So I'll quickly give an overview of what to expect from this talk. So Chucky would take over soon, and he'd go over what kind of aggregations we are doing and how we are aggregating data, some basic stuff over there, and then he'll deep dive into live aggregator architecture, that what are the nuts and bolts, how does it work, and then I'll go deep into our autoscaling mechanism, which is fairly sophisticated, and it helps us reduce our costs and scale without any human intervention. And since we are a startup, it's very important for us that we autoscale with minimal manual intervention. And then we'll talk about some specific applications of live aggregators that are allowing us to solve some real life problems in a very cool way. Okay, so I'll hand it over to Chunky.
Thank you, Usman. Good morning, guys. So let me start with a very simple exercise. So we have a basket over there with hundreds of balls of different colors. And what I basically want to do is to calculate how many balls are there of each color. So what I would do is I would ask one of you to come towards the basket and throw the ball one by one to me. So it would be a very easy task for me. But what if I ask each and every one of you to come towards the basket and throw the ball to me? I would do exactly what this guy is doing over there. I would save myself first. So doing counting or aggregation at scale is not easy. It comes with a lot of complexity. So at Mist, we have built a system which does aggregation in real time, which does aggregation at scale. By the way, there is no basket over there, so you don't have to come. So Live Aggregator is a distributed system which does processing and aggregation in real time. So let's understand what it does. So here you are seeing a total of 9 different messages coming in for a period of 17 minutes. And you can see each message contains a message ID, or you can call offset, client name, bytes transferred, and which organization that client belongs to. It is missed or home in this case. You can also see the snapshot of config files, which says, I want to calculate the number of unique clients for an org and total bytes transferred. So let's take a step back and process these messages one by one and see how the table on the bottom right you are seeing is being generated. So at time t equal to 0, the first message comes in from Sam, transferred byte 100, and org missed. So view would create a state. It would put this message. It says this is for org missed, and number of unique clients 1, and transferred byte 100. And at time t equal to 1, a second message comes in, but this time the message is from home. The org is home, not missed. So the view would create another entry saying this is for home, unique clients 1, and bytes transferred 60. So one thing you can notice is the time interval is from 00 to 10, because we have defined we want to do aggregation for every 10 minutes interval. So at t equal to 3, a second message comes in from org missed, and since this is a new user, so the number of unique clients now is 2. And similarly for org home, second message comes in, again different user, number of unique clients 2. And the total bytes transferred is 150 plus 60, which is 210. So in this example, we have seen we have maintained 2 time series, one for home and another for missed. And we did, or this view did, a total of 8 different aggregation operations. It did 2 operations for each message. First is calculating the unique, and second operation is doing the sum of total bytes transferred. So before going into details, let me first briefly give you some idea about few terms which we will be using during this presentation. So a view is basically a continuously running aggregator whose grouping column and aggregation info has been defined by the user based on what aggregation they want to do. Grouping column is basically a grouping key. Aggregation info gives you 2 information on which dimension you want to do the aggregation and what type of aggregation you want to do. And a time series is a series of data points for a grouping column in time order. And a partition is basically a stream of data coming in from Kafka. So this is a high-level architectural diagram of live aggregators, which starts with a user coming in, deploying a new config or a new aggregation, and then that configuration goes to Zookeeper. Once it is there in Zookeeper, the scheduler picks up, OK, I have this view, I have to run this view, and picks up that view from Zookeeper and packs them in an LA task and deploys it on the Mesos cluster. So each LA task consumes data or the stream of messages from Kafka. And as Osman mentioned earlier, we are using AWS pod instances, so we have to be fault tolerant. So this state, which we saw in our earlier example, that state is in LA task memory, so we checkpoint that state to S3. And for monitoring and alerting purposes, we emit data to SignalFX. And once the aggregation is done, we write the aggregated data to Cassandra, which is our main data store. But we do also write data to SignalFX, Kafka, or S3. That depends on the use case. And finally, it is the controller's responsibility to make sure that each view is running. It checks the Zookeeper. If some view is not running, it would just alert on call or tell that something is wrong and the view is not running for last X minutes. We can configure that time. So now let's dig in and talk about Live Aggregators Executor. It does multiprocessing. It spawns its main process, which is Kafka reader. It spawns multiple processes to aggregate the data. So the very first thing Kafka reader or the main process would do is to fetch all the views which it has to run in this LA task. And then it finds out from which Kafka partitions those views needs the data from. After getting that information, it creates one process, or it spawns one process for shared memory manager. And its sole responsibility is to share the messages which is being read by Kafka among all views. And it also spawns one process each for individual views. So here, process 3 and process 4 are the processes for those two individual views. So in this case, we can assume this task is running two views. So once the data is being read from Kafka by Kafka reader sends it to shared memory manager. And then it is shared memory manager's responsibility to share that message with both the views. So let's understand this with a simple example. So there is this message from Sam. When it comes in, Kafka reader reads that message and then send it to shared memory manager. Once it is there, it is now shared memory manager's responsibility to share that message with both the views. After getting that message, now the views start the actual work. Now they will start aggregating that data based on the message it received. So in this case, let's assume view number 1 is doing the aggregation, what we discussed in the last slide. And view number 2 is just calculating the maximum bytes transferred for any org by any client, for each org by any client. So view number 1 updated the state similarly, in a similar fashion we saw earlier, and view number 2 is just keeping the maximum bytes. So now let's see when second message comes in. It's being read by Kafka reader, being shared with shared memory manager, and then both the views. Now the views would read this message and update their state. So along with updating the state and processing the messages, each view is writing some data to Zookeeper. They write which Kafka offset they last processed, and what was the last time they processed any offset or any message, and various other information. And since these views state, they are in memory, we do checkpoint them to S3. We will see in a minute how that checkpointing is helping us. Once the aggregation is done, we write to Cassandra, or we write to other data stores, as I mentioned earlier. And for monitoring and alerting purposes and resource management, each process is writing data to SignalFX. Oh. OK, my executor is gone. Oh, right. As I mentioned earlier, we can lose any instance at any point of time. So the state we are keeping in memory can be gone at any point of time. So we have to be prepared for failures like these. So we have to be fault tolerant. So let's see what live aggregators would do in cases like these. So now executor is not running. So Zookeeper state is not being updated. So now controller will check, OK, this view or these views are not doing anything from last 10, 20 minutes, some configured minutes. And then it finds out, or it updates the Zookeeper that these views needs to be rescheduled again. They update Zookeeper, scheduler finds out, OK, I have these views, I have to run. So let's assume those two views are now again packed in a single LA task and being scheduled. They can be scheduled on different LA tasks, but let's for simplicity assume they are now again running on same LA task. So now the very first thing both the views will do before reading or processing any message, they would check S3. They would check if there is a checkpoint available for this view in S3. And if there is, they would fetch that checkpoint, update their memory, load the whole state in memory. And then the Kafka reader will now start reading from message 3. So this task or these views, they are not repeating any work. They are not duplicating the messages read from Kafka. We are trying to minimize that as much as possible. So you can see here, checkpointing is the key for failures like these. So now you can ask one question, or you might be having one question, that why these guys are doing multiprocessing in this task. So there are two main reasons. First is we want each and every view to not read from Kafka. We want the message which is being read from Kafka to be shared among multiple views. For the reason, we don't want our network out of Kafka cluster to spike or to increase. So in this case, these two views are sharing the same message which is being read from Kafka with the help of shared memory manager. And the second reason is resource management, which Osman will talk about later. So now let's talk about the scheduler. Scheduler is a lightweight component of our system. We have implemented it to just do one simple task of scheduling the views with minimal possible constraints. So let's see how it works. There are three views in Zookeeper, view 1, view 2, view 3, which needs to be scheduled. They are in waiting state. The Zookeeper manager finds out, OK, I have these three views. They will pick those views, put them in a queue, and then task manager continuously fetches views from the queue, and then puts them in a task, packs them in a task, creates an mesos executor, and then schedules it on the mesos cluster. So there are two main constraints which the scheduler needs to consider. Number one is we do not want views which are consuming from different partitions to be in the same LA task. So in the second case, if the second case happens, then the task manager would just create two LA tasks, put view 1 and 2 in first one, and put the third view in the second one. And the second main constraint is how many tasks the scheduler or the task manager should put inside one LA task, or how many views it should put inside one LA task. And that depends on how many resources the scheduler has received from mesos and how many resources each individual view needs to be executed. So Osman will talk about the resource management of this later in the slides. Now let's talk about some numbers. Now let's look at the scale Live Aggregator is running on. So we are consuming, or Live Aggregator is consuming around 480,000 messages per second during peak times. And that is being read directly from Kafka. And the other number you are seeing on the right, which is of 620,000 messages per second, this would be the number read from Kafka if each individual view is directly reading from Kafka. So you can see we are saving around 30% of network out on Kafka by sharing that message inside a view. So in our early example, we saw there were 2 time series and 8 aggregation operations. But in total, Live Aggregator at peak times is keeping more than 300 million time series, and it does millions of aggregation operations during our peak times. And since each view is keeping the state in memory, so across all the views, we are keeping more than 2.5 terabytes of data in memory, and they are writing billions of entries to Cassandra every single day. So now Osman will talk about how we have been continuously scaling from last 2 years and how we will continue to scale in next more years to come. Thank you.
Okay, guys. So in my experience, some of the things that I've noticed in the past few years about distributed systems is that there are these 3 properties that if a distributed system doesn't have, it's not likely to succeed: reliability, cost effectiveness, and scalability. And like I mentioned previously, we are using Amazon Spot instances. I won't go into too much detail about it because we've discussed it at previous Strata conferences as well, so I don't want to repeat the same thing again. But we are running our infrastructure extremely cheap compared to most other companies who are operating on Amazon. like I mentioned, we're using more than 80% of our production data center is Spot, which is 70% less than even on even the reserved cost. What I'm going to cover is scalability primarily. How are we auto-scaling? Because we are a startup, and since I've been in this company, well, actually not even that. Even in the last year or so, our scale has increased by almost an order of magnitude. So I'd be talking more about reliability and scalability for the rest of the talk. So one thing I started following 4 or 5 years ago when Netflix came out with Chaos Monkey, and it was an amazing tool. I was inspired by it because that for me was kind of the start of chaos engineering. I loved the concept of arbitrarily terminating servers, but I was using it in one of my previous jobs as well. One thing that I'll often do is when there are problems going on in the infrastructure, the first thing we'll do is stop Chaos Monkey, and that for me was that was defeating the point. And for that reason, I call Chaos Monkey as controlled chaos. I can stop it, I can resume it. When the going gets tough, you can always stop it. And for me, that defeats the purpose of truly making sure that your infrastructure is reliable. So Amazon Spot instances come very handy in this case because, of course, they save you cost, but to be honest, I don't primarily use them for reducing costs. That's a good byproduct. I use them because they force you to be reliable. You go into a world where you cannot control the chaos, and not even Amazon controls it. It's controlled by the people who are using Spot instances, supply and demand, just like the stock market. So, there are actually days where sometimes it's difficult to believe that what we are doing is even possible. So just to give you some perspective, we track how many instances terminate every 5 minutes. This is an aggregated number of how many Spot instances we lose over the course of a day. And as you can see, recently there was a week or so where we lost 800 instances in a single day. That's even bigger than our production data center. And that's probably like we recycled our entire production data center, barring a few machines which are not on Spot, almost like 2 times in the day. However, when you're living in such volatility, one thing which is extremely important for real-time applications is that you don't fall behind real-time. And for that matter, we have live aggregator controller that keeps track of how good we are doing for every single view that's running there. So it's a very simple, straightforward concept. We keep track of the message that was most recently produced by the external devices, and we take their timestamp. That is the most recent message that we got, and then we take into account the most recent message that was processed by live aggregators. And the difference between the timestamp is something which we refer to as lag. So like in this example over here, there are these 4 messages. The most recent was at 5 p.m. The previous one was at 4:59:55 seconds. Basically, message 3, if my last message that I processed was message 3, then I can say that I am lagging by 5 seconds. So keeping that in mind, let me show you something from our production data center. So I don't remember this date. It's like somewhere in July last year, May last year, when there is this particular view that is running on an Amazon Spot instance. At around 10 o'clock, the machine goes away. And the lag, which is the y-axis over here, you can see that once the machine terminates, the lag starts to go up because the messages are queuing up, you're not doing anything about it. The scheduler realizes that that view is no longer running. It goes back and restores the checkpoint, and that's why you see this sudden jump, because we checkpoint every 10 minutes for most of our views. So it restores the checkpoint from 10 minutes ago, and then it starts processing messages, and slowly the lag goes away. We, like I was talking about it earlier as well, we've seen tremendous growth over the last year. And it is almost impossible for us to have someone sitting on next to the system and increasing the resources every once in a while, because as you can see, we break record every day. Like whatever traffic we saw on a Monday, we're going to see more traffic on a Tuesday. So we have two things to cope with over here. One is the trend, the overall trend. We are increasing load every single day, and also there is seasonality to it as well. During the days, we'll have a peak in the load. It'll go away, and then the evening, that high load comes back. Something which comes in handy is right sizing of containers, and Live Aggregators is running more than 1,000 containers at the moment. So just like this cat is, if you try to fit this cat in this container over here, she'll have problems doing that. And you can give this cat a big enough box, and then you're wasting resources. So you need to find the right box to keep this cat in. And for the rest of this talk, I refer to it as right sizing containers. So this is the executor diagram that Chunky showed earlier. One extra thing which he didn't cover over there was the resource manager part. So in order for us to do effective load balancing, it is extremely important to measure how much resources are you consuming. Like in the previous slide, if you don't know how big the cat is, you can't find a box to fit the cat in. So we're using psutil, it's a Python library. We're using psutil to measure fine-grained metrics for the CPU utilization of each of the processes, as well as the memory utilization, and those are the two main dimensions that we are considering for the time being. So what this resource manager does is, it measures the CPU utilization for each process that's running. Like for example, in this case, view 1 and view 2, they are running, they're using 0.8 cores and 0.6 cores each. Similarly, the shared memory manager is using 0.2 cores. But the important thing over here is, previously you've seen that the job of the shared memory manager is to take messages from the Kafka reader and then distribute them amongst the views, which means that the resource usage of shared memory manager is depending on how many views it's serving. So basically this 0.2 number, if you consider it's running 2 views, it's basically dedicating 0.1 cores to serve each of these views. And then the Kafka reader in this example takes 0.2 cores. So in total, this task is consuming 1.8 cores. Resource manager will keep track of all of these numbers, and then keep and checkpoint all these numbers in Zookeeper, because Live Aggregator scheduler, it's very important for the scheduler to keep all these numbers into consideration when it's packing views into tasks. So I'll just continue the previous example. So given that these are the numbers for how much resources, how much cores each of these views need, let's say that Mesos offers a scheduler 2 cores. What we'll do is, the task manager will initially say, okay, I need to consume from this Kafka partition, so I dedicate 0.2 cores to it, so I have 8 cores left. The next thing I'll say, I'll go to the view queue, and I'll say, I can run view 1 because it needs 0.8 cores, and yes, I need to pay the shared memory cost, which is 0.1 per view. So now you're left with 0.9 cores. It takes the next view from the queue, and now you're left with 0.2 cores. At this time, it cannot include view number 3, so that view will have to wait for another offer from Mesos to the schedule, and that's when it gets scheduled. But after that, the task manager schedules that task, and it starts running on one of the Mesos servers that we have. So the important thing over here is, we have all these numbers, but these numbers change. Like I showed in the previous load diagram, these numbers change over the course of a day, and there's a long-term trend as well. So let's say if we got these numbers from the evening load, which where the load for us is typically low, the load might not be the same the next morning. So, and the load is changing with every given hour. So what we end up doing was, we defined a metric which we call as line factor. And the lying factor is the difference between how much resources you are reserving for a container and how much resources the container is actually using. So reserved minus actual, a positive number over here means that you have over provisioned the container, meaning there are more resources reserved than what it actually used. And on the other side, a negative number means you are reserving less resources than what you are actually using. So like in the morning, the load increases on all of these components, and the lying factor becomes minus 0.4, which means you are creating trouble for other containers living on the same VM or the Amazon server. So another thing over here that's worth noticing is that our autoscaling policy is based on keeping the lying factor within a band. If you're going, let's say, if you're going above this line, it's a positive number, you're wasting money because you're over provisioning containers and they're not making use of those resources. But on the other hand, if you are below 0 or if your lying factor is negative, you are causing, you can potentially cause fires in the system by contending for these resources. These are the lying factors in real time for possibly 1,000 containers from a few days ago. And in production, our thresholds keep on changing, but at the time we took this picture, the upper threshold was 0.2 and minus 0.05. So minus 0.05 means that we do allow containers to once in a while, draw more juice out of the cores than what they subscribed for, but we won't allow it in long term. And so this line over here is a container which is a very well-behaved container. It keeps, the lying factor doesn't increase, and it doesn't have a problem. But here's a container for which the lying factor decreases over the course of the morning, and it goes to minus 0.05. That's when this container commits suicide. So the resource manager knows that the scheduler reserved 1.8 cores for me. So if it starts taking, let's say, 2.2 cores in the previous example, the resource manager will tell the task to basically commit suicide. It'll say, update the resource requirements in Zookeeper, and then kill yourself because you are creating problems for other containers. And I've spent a few years now in DevOps. We talk a lot about noisy neighbor. Honestly, any time that we don't understand what's going wrong, we just say it's a noisy neighbor. But this actually is a noisy neighbor. You are allotted, and this GIF over here represents the problem very well. So this guy has a reservation for a small hand carry in the cabin, and he's yet trying to get something very big. He's not getting things done for himself, but he's causing a lot of problems to his neighbor as well. And that's what this container was about to do had we not killed him. And similarly, when the load goes away, the lying factor starts increasing, and once it reaches 0.2, the container commits suicide once again. And when it commits suicide, it updates its resource numbers, and the scheduler will give appropriate amount of resources to it. This is a graph that shows the amount of cores reserved versus the actual usage, and as you can see, it's the reserved cores follow the actual usage pretty well. So at any given time, we are not causing problems for other containers which are hosted. And the good thing is, in the last probably around a year or so, we have the number of cores that we've used on this cluster. It has increased from basically by an order of magnitude, and we did not increase the resources manually. Of course, we have bugs, and we do figure out how to solve those bugs, but it's been scaling up really well on using the autoscaling. And since I have not a lot of time, let me quickly go over. There's a cool application that we came up with. So like I said, we do indoor location, and this map over here is our office map, and we were interested in getting a heat map of how many unique devices pass over this are in different parts of our office at different points in time during a day. So each of these device, each of these device reports its location every second, and those locations are going into Kafka. And because there's a lot of data coming in since we have grown, we have partitioned those locations into different Kafka partitions because one aggregation task cannot handle it. So we divide the whole map into a grid, and then what we do is the basic location topic, which is giving us the input. All the clients are divided into 3 different partitions. So basically, we get the unique count over the map from 3 different partitions. So these represent the partial sums, the partial unique counts for the map. And what Live Aggregators allows to do is we read from a Kafka topic the organic data which is coming from the users, and then we write these results back, because we're going to do a multi-level aggregation, which is then going to read from topic 2, which has these partial sums, and then aggregate again all of them in one place. What that fetches us, it makes our system extremely scalable, because we can theoretically have like hundreds and hundreds of partitions, and we can reduce them just like in a tree form over into one grid. And here's a video from it that that resulted from it. So this is a school, and we were looking at the heat maps for different organizations. And it doesn't show really well on the projector, because on the computer you can see the yellow parts. But this gives you an idea of where the devices are, where the foot traffic is, and yeah, we are planning to make this part of our product. It's still early days for it, but we're working on it. So for future works, we are looking into joining streams, like what if I can combine the location data with your, let's say, your Wi-Fi experience, and we can figure out that in this corner the Wi-Fi is not good and stuff like that, because Wi-Fi people, they care about it a lot. And we're planning to do some intelligent resource scheduling. We currently are in Python. We also want to port it to Go, because it's much more efficient using Go. That's what I've realized after implementing the whole thing in Python a couple of years ago. And yeah, please rate the session. Give us any suggestions if you feel about Live Aggregators, about the talk itself. And yeah, we are ready for questions.
On that day where William was shut down, what happened to Kafka? Is it running on its reserved instance, or what happened to it?
No, so our Kafka clusters, they are.
So the question was that on the day when we showed the spot volatility, what happened to the Kafka clusters?
So our Kafka clusters, they are not running on spot. They are running on reserved instances. So we are running all of services, our topologies, and this also comes under one service on the spot instances. Our Kafka or Cassandra cluster, right now they are not running on spot instances.
How many days can you survive without having any spot instances?
Sorry, so the question is, how many days can we survive?
I don't know, it looked like it was the whole day, but how many days was that spot instance thing, and how much can you survive on a Kafka before running out of all the instances?
So typically the way spot instances work is, when you see that 800 instances went away in a day, that doesn't happen in a single 5-minute period. So the way, from what I remember, the way this specific event happened was, we lose 10 instances every 5 to 10 minutes. So what we do, when we use spot instances, is we always keep excess capacity. So let's say I'm keeping 10% excess capacity, and at any given time I lose 5% of the capacity, so I still have access capacity to move the workloads to, and in the meantime I get new instances. So the 800 machines going away, that does not mean that our compute reduced. Like if we were, let's say, running 1,000 instances, this does not mean that at any given time we went to like 200 instances. All it means is they're recycling, and over the course of a day we lost 800.
And since, okay. Oh, okay.
Okay. Any other questions, or feel free to. We're going to hang out outside if you have any other questions.
Thank you, guys.
Thank you.